Welcome everyone to the 5th Developer of the Year Michael Wormit Award. About 5 years ago, on March 14 of 2015, the life of Michael Wormit was cut short. It was and still is a tragic loss for all of us. Michael was a husband, a son, a friend, a great colleague, and a great mentor. He was also a part of Q-Chem developers community. We gather here today to remember Michael and to celebrate his accomplishment and his contributions to our community. His life was short, but he left a mark, and his work will continue to make an impact. And this is something which we should cherish and remember. To commemorate Michael's contribution to Q-Chem community, Q-Chem Board of Directors established an award in his name. On behalf of the Board of Directors, let me introduce Michael Wormit's Award. The award has been established in August 2015 to recognize excellence in developing new methods and algorithms in the area of electronic structure and implementing these methods in state-of-the-art computer codes within Q-Chem Open Teamware Community Project. The award is given annually, and it includes a certificate, which I will show you soon, and $500 prize. By this award, Michael is remembered for developing state-of-the-art algorithms and computer code for many-body methods and for his leadership in community building, education, and mentoring of junior team members and infrastructure development. Any member of the Q-Chem developers community is eligible for this award, and the selection criteria are scientific innovation, excellence in code development, contributions to infrastructure and developers community. The first award was given in San Diego in 2016 to Evgeny Epifanovsky, and in 2017 to Andrew Gilbert, 2018 Alec White, and to Yonho Lee in 2019. Today, the 5th Michael Wormit Developer of the Year Award will be presented. We have received several outstanding nominations. The board appointed an international selection committee. The committee has chosen 2 winners, as this year is an exceptional year. And the winner of the 2020 Developer of the Year Wormit Awards are Dr. Yuezhi Mao and Dr. Pavel Pokhilko. I will introduce them separately, but please join me virtually in thanking Yuezhi and Pavel for their contribution to the company and to the community, and congratulate them on being selected as the recipient of the 2020 Developers of the Year Michael Wormit Award. The first speaker today is Pavel, and this is a certificate, Pavel, you will receive, signed by Anna Krylov, the president of the Q-Chem. And let me briefly introduce Pavel. Pavel graduated from Moscow State University with honors. After that, he moved to University of Southern California for his PhD under supervision of the Anna Krylov. The nomination of Pavel was mainly based on his work at USC that includes implementation of multiple features in Q-Chem. The selection committee especially cites the development of single and mixed precision coupled cluster codes, spin orbit couplings EOM-CC, frozen natural orbital approximation for open shell systems, new localization library, and effective Hamiltonian for magnetic property. Pavel not only develops Q-Chem for his project, but also helps other research groups to interface with Q-Chem and integrate their codes into Q-Chem. A short quote from the nomination letter by Anna Krylov I rarely have a chance to enjoy such a stimulating discussion about science, even with postdocs. So I hope postdocs are not offended. Pavel is now a postdoctoral fellow at Professor Zieg's group at University of Michigan, working on the application of Green's function method to a strongly correlated system. And today, Pavel will talk about from single molecular magnets to infinite spin chains, a many-body adventure. Pavel, the floor is yours.
All right, excellent. Today I'm going to talk about molecular magnets, about molecular systems. I will start from single molecule magnets, and then I will talk about bulk magnetism. I will talk about infinite systems. Why I was interested in single molecule magnets or in magnetism in general? It is these materials can be used in electronics and they can be employed in many devices. So single molecule magnets specifically are very lightweight and therefore they can be used for novel memory types, and over several recent years they received a lot of attention because they can be used as building blocks for qubits. Single molecule magnets are tunable because we can replace metal centers that exhibit magnetic properties and ligands and change the way how these molecules respond to the magnetic field. And theory can guide experimental studies in the designing of these systems. So experimentally, these systems are usually described through some model Hamiltonians, such as the one shown here, Heisenberg Hamiltonian. Here, J denotes an effective exchange constant, and local spins as A and as B describe the open shell electrons on radical centers. But from a theoretician's point of view, this Hamiltonians looks a little bit like this. There is some effective quantity, effective local quantity on one center interacting with another effective operator on another center through some effective interaction. In rigorous ab initio description, all the wave functions are very multi-configurational. They have a lot of contributions. And we have to work very hard to rub them into this effective form. I will talk a little bit how we do that. We have to face challenges describing both strong and weak correlation. And we do that through equation of motion coupled cluster ansatz. First, we pick a determinant that we pick a reference determinant that describes a reference state well. We can pick either a closed shell determinant or an open shell determinant. Then we solve a weakly correlated problem for it, and we find coupled cluster amplitudes describing the reference state. Then we solve an eigenvalue type of equation and find linearly parameterized operators that act on this reference state and generate all other states. In UMCC ansatz, we have a lot of freedom of how to choose this operator, and different flavors of it will give different variants of the methods. For example, we can pick electronic excitations, and in this case we will obtain descriptions of the electronically excited states, and this variant of the methods is called EE, methods for electronically excited states. We can pick spin flipping operators, and in this case we will obtain the electronic states that differ from the reference state by the spin projection. And this variant of the method is especially useful for single molecule magnets because it allows to access different spin manifolds, and it allows to access multiple open shell states. We can also change the number of electrons. If we remove 1 or 2 electrons, we get a method for ionization potential or double ionization potential if we remove 2 electrons. Or we can attach electrons, and this leads to electron attachment variant of the methods or double electron attachment variant of the methods. These methods are also useful for strongly correlated systems because they can access electronic states with different orbital occupations. Now, it turns out that magnetism phenomena is much more complicated because we often have to deal not only with non-relativistic Schrödinger equation that leads to isotropic magnetic Hamiltonians, but we often have to deal with relativistic effects that can lead to magnetic anisotropy and anisotropic Hamiltonians. So one of the most important relativistic effects is spin-orbit interaction. It has 1 and 2 electron terms, and this Hamiltonian is spin-dependent. So we have to think how we deal with the states of different spin projection. So the electron part of the spin-orbit operator is very bulky, so it's common to introduce some approximation. We use spin-orbit mean field, which is very accurate, and we don't impose any additional approximation. Effectively, it looks exactly like the 1 electron part, so we can apply the algebra that we use for 1 electron part. But effectively, we will treat 2 electron part well. And we have to deal with different spin projections. So how do we do that? If we want to compute spin-orbit couplings as a transition property, we start from computing transition density matrices as we usually do in calculations of transition properties. Then we use Wigner-Eckert theorem to extract the reduced matrix element out of the transition density matrix, and this matrix element does not depend on any spin projections. Then we contract it with integrals, and thus we obtain the reduced matrix elements that do not depend on spin projections, and we use Wigner-Eckert theorem again to compute all possible matrix elements between the multiplets with any spin projections. This algorithm is ansatz agnostic, so it can be used for different methods, and currently we interfaced it with EMCC, EMMP2, core valence separated EMCC, and RAS-CI. So how can we use it in molecular systems? So here I would like to share with you one of the examples. This is a single molecule magnet. It is an iron complex. So this is iron, and it is surrounded by bulky ligands. And we can start from the hex state reference state. It has an alpha electron on each of the d orbitals. This electronic state is weakly correlated, and it is well described by only one reference determinant. So it is convenient to pick it as a reference state, and we add just one electron through UMCC ansatz, and we can add it to different d orbitals. So we can add it either to the lowest orbitals or further, and we can obtain a balanced description of multiple quintets. These quintets can interact through spin-orbit interaction that splits the ground state. So here I show how the ground state splits. Because of the symmetry of the system, spin projection as Z is preserved, and you can see that it forms some sort of a barrier, that in order to go from the lowest state on the right to the state on the left, the system has to go through some barrier. So this situation can be described by an effective Hamiltonian of this type as ds, where d is a tensor. It's called single ion anisotropy, and its name perfectly fits the situation that we have here. We have only one transition atom. And if we compare our calculations with the experimental results, we see a very good agreement. So from that, we can think that we indeed are on a good track in computing of these properties. But sometimes the life is not easy, and for both theoreticians and experimentalists. And one of the very challenging systems is copper oxalate. It is an infinite system, so it is a bulk antiferromagnet, and its crystal structure consists of chains that are assembled together. So you can see the fragments of these chains on the right. Experimentally, it is a challenge because it's not very clear how to interpret the experimental measurements. There are groups that interpret the magnetic measurements in terms of dimeric models, and there are other groups who interpret their measurements in terms of infinite spin chain models. And it's not very clear which magnetic structure this compound has. Here, theory can resolve this puzzle and resolve the battle. So, but how can we treat the infinite number of spins? The system seems to be way too large and way too strongly correlated. We can build an effective model for that. So first, we start from the very detailed description of the system that we can obtain through UMCC. We can obtain the description of strong correlation and weak correlation. We see all the determinants that contribute to the wave function. And we have a good description of the energies and properties. And then we can map it into model wave functions and model Hamiltonians. Mathematically, such transformation is described by a Bloch formalism, where omega is a mapping operator. So it allows us to formulate an effective theory in the model subspace without any loss of quality, without losing any quality of energies or physical observables. And then we can work with this model Hamiltonians as suggested by Nick Mayhall and Martin Gordon a few years ago. We can expand it to the states that we cannot easily tackle in UMCC approach. So here we generalize this procedure and we extrapolate this Hamiltonian not only for the states that we cannot tackle, but also for the infinite number of radical centers. And from that, we can build the effective Hamiltonian and validate its form. So, and here how it looks like. So if we take the fragments of the chains that we use for our calculation, we see that indeed it looks like a Heisenberg Hamiltonian. So here the numbers in blue are the nearest neighbor couplings. The numbers in red are the distant couplings. So we see here several things. First of all, we see that all the interactions are mainly local. So so we see that the couplings between distant centers are very small. They're less than one wave number, which is very comparable to the thresholds that we use in our calculations. Then we also see that the numbers don't change much. So we see that the effective exchange coupling between nearest neighbors converge very rapidly. So we can use that to build our model. So from that we can derive a model for this compound that looks exactly like the isotropic Heisenberg model for the infinite spin chains. And this is very nice because infinite Heisenberg spin chain is one of very few quantum integrable models. That means that it has an exact solution given by beta ansatz. Many properties are well known. So although there are some mathematical questions about this model, many physical properties of this model are well known, including magnetic susceptibility. So we can compute magnetic susceptibility based on the infinite spin chain Heisenberg model. So if we just take the exchange coupling from the spin flip CCSD effective Hamiltonian, then we see a qualitative agreement with the experiment. We see an overestimation in the strength of magnetic susceptibility and some underestimation of the position of the maximum of magnetic susceptibility. But we can improve the description. We can include perturbative triples, and we see that they have a big impact. So with perturbative triples, we see that the agreement becomes much better. Then we can include spin-orbit effects. Spin-orbit interaction not only splits the levels, but also shifts them. And this is exactly what happens here. And we also can include basis set effects. We can improve the basis set, but we see that here the basis set does not change the value of the coupling much. And once we sum them up, we observe an almost perfect agreement with the experimental results, and we see that we almost approach the experimental error bars in magnetic susceptibility measurements. And from that, I would like to acknowledge people who really influenced me in my PhD work. First of all, I would like to thank Dr. Anna Krylov, my PhD advisor, who guided me through science and who changed the way how I think about science overall. I would like to thank Dr. Evgeny Epifanovsky, who guided me through the Q-Chem code and who explained how to use it and how to develop it. And I also would like to thank Boson for emotional support. And from that, I would like to answer any questions.
Thank you very much, Pavel, for this very educational talk. And there are also two areas that are set up in the Q-Chem forum for question after this webinar is over. You can still ask questions from the speakers and they will respond on that forum to your questions. So there is a question, Pavel. What is the reason that weak correlations are so important in these systems?
So yes, indeed, we see that weak correlation is important, and it's not only in copper oxalate that I showed you, but also in a few other copper systems. And this has been observed not only by us, but also by other studies. For example, there is a study from Frank Nize about copper acetate, who also found that weak correlation is extremely important. But I think more work is needed to answer this question because it is not very clear why this would be the reason.
Okay, great. So it actually stimulates more research. The second speaker and the awardee is Dr. Yuezhi Mao. And I'm going to briefly introduce him. Yuezhi Mao received his Bachelor of Science degree in Material Chemistry from Peking University in China in 2012. Then he joined UC Berkeley working with Martin Gordon, and he received his PhD in 2017 in December. The nomination of Yuezhi was mainly based on his PhD at UC Berkeley. His work includes development of crucial infrastructure for Q-Chem, namely fragment methods and Gen-SCF-Man. The selection committee specifically cited his infrastructure as a significant step toward implementation of new advanced features in Q-Chem, such as second generation of energy decomposition analysis based on absolutely localized molecular orbitals, which he is going to briefly maybe talk today about that, the adiabatic EDA, improvement of constrained DFD, and many, many more. More importantly, Yuezhi has supported other developers generously with advice as well as personal time and effort. A short quote from the nomination letter by John Herbert. Yuezhi is by a wide margin the most active developer who is not a Q-Chem employee. So thank you very much. Yuezhi is now a postdoctoral in Professor Tom Markland's group at Stanford, and his current research focuses on the study of non-adiabatic processes in the gas and condensed phase using electronic states obtained from ab initio calculations. Today, Yuezhi will talk about electronic structure method based on absolutely localized molecular orbitals from non-covalent interaction to electron transfer. Yuezhi, the floor is yours.
It is my great honor to receive the Michael Wormit Award, the Michael Wormit Award this year, and I would like to thank Q-Chem for organizing this virtual symposium, which gives me the chance to share my research. Today, I will focus on my development of electronic structure methods based on ARMOS. I will show how this method can facilitate the study of non-covalent interactions and electron transfer. So the ultimate goal of my research is to unravel chemical mechanisms to facilitate the rational design of new catalysts and functional materials or molecules. And in particular, I'm interested in two research topics. One is non-covalent interactions, because they offer a new route to enhance chemical reactivity by modifying the non-covalent interactions in the system. One can modulate the energy profile of chemical reactions. And the second is electron and hole transfer. They form the fundamental steps in many chemical processes, such as photoredox catalysis shown here. And my method development will aim to address the challenge to unravel the mechanisms behind these phenomena or processes and to harness them in chemical applications. And before we dig into the first topic, I would like to give an overview of the technique the core technique for all this method development, which is absolutely localized molecular orbitals. So ARMOS are molecular orbitals assigned to fragments and expanded in the basis functions on the assigned fragment only. So they are quite different from like the case of a standard SCF calculation. So in a standard SCF calculation, there is no partition in the system. So the molecular orbitals are expanded in the basis function of basis functions of the full system. And in the SCF procedure, the global occupied virtual partition is variationally optimized. And also, if the system is charged, then the charge will be delocalized in the full system because there is no mechanism to enforce charge locality here. While in the ARMOC setup, we will introduce the concept of molecular fragments, and then the molecular orbitals are expanded in the basis functions on the assigned fragments only. And in the SCF procedure, the occupied virtual partition is optimized on each fragment rather than being optimized globally. And also, you can prove that in an ARMOC calculation, the molecular population of each fragment will be conserved, so charge locality can be enforced. And using ARMOS, I have developed a family of methods which can be used to study non-covalent interactions. They can not only decompose intermolecular interactions in closed shell and open shell systems, but also the decomposing changes in molecular properties, such as vibrational frequency shifts induced by non-covalent binding. In addition, in collaboration with Professor Yihan Shao, I have developed ARMO-based analysis for unraveling substituent effects on conjugated systems, on the frontier orbitals of these conjugated systems. And today I will focus on the second generation ARMO EDA and its recent extension to the solvation environment. So energy decomposition analysis is a family of methods which separate a total interaction energy into physically intuitive, meaningful terms. And these methods are particularly good at interpreting phenomena related to non-covalent interactions. And so the ARMO EDA method essentially provides a physically intuitive path connecting the isolated fragments and the fully relaxed intermolecular complex. So we start from the isolated fragments whose orbitals are optimized separately with fragment SCF, and then we bring them together into the complex geometry without relaxing their orbitals. The energy change of this step will define as a frozen interaction. Then we allow the orbitals to relax on each fragment, and this energy lowering will be the polarization term. And finally, we remove all the constraints and allow the charge to flow between fragments, and the final energy lowering is defined as the charge transfer term. And more recently, we introduced the second generation of ARMO EDA for DFT calculations. And in this method, we enabled the further decomposition of the frozen term into physically more intuitive electrostatics, Hall repulsion, and dispersion contributions. We also introduced a more robust scheme to separate polarization and charge transfer. So with the second generation ARMO EDA, we are able to identify the fingerprints of many different types of non-covalent interactions. Here is an example of the adenine-thymine complex, and for the hydrogen bonded and the pi stacked configurations, you can find the dominating interaction component are quite different. And with the ARMO EDA, established in the gas phase is highly desirable to extend to enable its use in the solvation environment. This is because there are so many interesting chemical processes occurring in the condensed phase rather than in the gas phase. So we recently developed a method called AMO-EDA solve to consistently include the solvation environment in an AMO-EDA calculation. And so the goal is to decompose the interaction energy in the solvation environment, which is energy difference between the fully solvated complex and the sum of the solvated fragment energies. And as in the gas phase EDA, it can be decomposed into frozen, polarization, and charge transfer components. And for the frozen frozen term, by playing a small math trick here, we can further decompose that into a new term, which is called delta E sol, which describes the change in the solute-solvent interaction energy upon the formation of the complex, as well as the decomposition of the frozen interaction energy as evaluated in the gas phase. And then by separating the electrostatic and the non-electrostatic component of the solute-solvent interaction and combine them into these terms, we are able to achieve a frozen energy decomposition in the solvation environment. And then we perform AMO and standard SCF calculations in the presence of solvent. So in the calculation of polarization and the charge transfer, the solvation effect will also be taken into account. And first, we would like to validate this method on a simple system, which is a water-sodium complex immersed in different solvents. And here the solvents are modeled by the SMD solvation model, which contains a PCM description for the electrostatic interaction and some non-electrostatic terms. So here, by comparing the results in toluene and water, we found that the electrostatics and polarization are more strongly screened in the more polar solvent, which is intuitively correct. And also we found that the unscreened electrostatics is elect 0. So this dashed line is more attractive in the more polar solvent. And this is because the dipole moment of the water will be larger in the more polar solvent. And if we look into the solute-solvent interaction contribution, we found that and decompose that, we found that in this case it's dominated by the electrostatic interaction, and the non-electrostatic component is of minimal importance in this example. And these all look quite reasonable to us, and we are going to apply this method to study like a complex in CO2 reduction catalysis. And so this iron TPP and its derivatives are a prominent family of catalysts for CO2 reduction to carbon monoxide. And once FeTPP is doubly reduced, it can activate CO2 by donating an electron and form an adduct like this. And in previous experimental studies, it was found that by introducing different substituent groups to also or para position of these methyl-phenol groups, one can significantly modulate the catalytic performance of these catalysts. So for example, by introducing the trimethyl amino group, which is a positively charged substituent to the para and also positions, it can achieve higher catalytic activity at low overpotential, which is certainly favorable. And this similarly can be achieved by introducing a hydroxyl group to the also position here. However, by introducing a negatively charged group to the para position, such as this sulfonate group, the catalytic performance will degrade. So it was conjectured that the through space interaction between, For example, these positively charged groups and the CO2, the through space interaction can stabilize this activated CO2, which lead to favorable catalytic performance. And we are using ARMO-EDA solve to further investigate the mechanism for this modulation of catalytic activities. So here are the results of these substituted complexes and relative to the unsubstituted one. So this is a differential EDA results. And the result is quite surprising to us because what we found is electrostatic interaction between the positively charged TMA groups and the CO2 is actually strongly attenuated in solution. So for these two, they are not significantly favorable at all. And for this para-TMA complex, this is even less favorable than the unsubstituted complex, which is quite counterintuitive result. And we found that, in fact, the stabilization achieved by these TMA groups through structure mechanism rather than through space, because this is because the TMA groups it's a very strong electron withdrawing group, so it can reduce electron density near this catalytic center and then reduce the repulsion with negatively charged CO2. And on the other hand, for the also OH complex, if we look at its the fingerprint of this interaction, we will find it's very similar to a typical hydrogen bond, and this is indeed through space hydrogen bonding, which stabilize the activated CO2. So what can we learn from these results? So we firstly found that introduced positively charged groups to stabilize CO2 minus may not be that effective in solution because of the screening. And on the other hand, if we can effectively squeeze out the solution and get rid of this damping effect, we might still be able to stabilize the CO2 minus. And so based on that, we designed this new complex, which contains this quite bulky and floppy ligand, and it carries a positively charged methyl imidazolium ring. And we found that this new complex is able to enhance the stabilization of CO2 mainly through the electrostatic interaction. So it's substantially favorable here. And our further study shows that this comes from two different sources. One is hydrogen bonding between the amide group and the CO2, and the second is from the positively charged imidazolium ring. And because this second coordination sphere ligands are quite bulky, they can effectively squeeze out the solvent and achieve very large stabilization from electrostatic interaction. And based on the established correlation, this complex can potentially be a very ideal catalyst for CO2 reduction because it achieves the largest stabilization by far. And besides investigating non-covalent interactions, I have also developed method based on ARMOS to create diabatic states to facilitate the study of electron and hole transfer. And now we are going to enter the second topic. So electron and hole transfer are fundamental steps in many chemical and biochemical processes, such as charge and energy transport in photovoltaic materials. These two processes are essentially the same, but they are called differently simply depending on whether the system is negatively or positively charged. And the charge localized diabatic states naturally correspond to the initial and the final states of the electron hole transfer process. For example, for the hole transfer in this ethylene dimer, the two diabatic states will correspond to the charge localized on either of the ethylene molecules. And these chemically intuitive diabatic states form the basis form the basis of widely used rate theories, such as famous Mach theory and many quantum dynamics approaches. However, these diabatic states are not naturally produced by electronic structural calculations, and the special treatment are needed, which are the diabatization schemes. And our goal is to develop a DFT-based diabatization approach, which can give variationally optimized diabatic states and get easy access to the associated nuclear forces. And we also hope to evaluate the couplings between the diabatic states accurately and also produce consistent results for asymmetric systems, because this is not satisfied by some of the available methods. And we use ARMOS again to construct these charge localized diabatic states. So here we consider a whole transfer system as an example. And we can construct these ARMOS states from fragment orbitals. For the initial state, we have a positively charged donor and a neutral acceptor. So, and we can perform SCF calculations on each of the fragment separately and then concatenate their orbitals. This is initial guess to the initial state for the electron transfer, whole transfer here. And for the final state, we can do something similar. We just need to switch the population of the two fragments and do the fragment SCF and then concatenate their orbitals. Then we just launch the ARMO SCF calculations, which will give us variationally optimized diabatic states. And now we want to accurately calculate the coupling between ARMO-based diabatic states, and so the coupling between two symmetrically orthogonalized ARMO states can be determined using this equation, and it will require the diagonal and off-diagonal elements of the Hamiltonian matrix in the non-orthogonal ARMO state basis. So we can use a multi-state DFT approach to calculate these matrix elements. So for the diagonal elements, it's quite intuitive to use the Cohen-Sham energies associated with each of these diabats. And for the off-diagonal elements, the original MS DFT method first calculates the coupling between two Cohen-Sham determinants using Hartree-Fock Hamiltonian, and then apply a correction for the exchange correlation contribution, which is estimated as the average of the energy difference between Cohen-Sham and Hartree-Fock for each determinant. However, we found that this method systematically overestimates the diabatic couplings in most of the hole and electron transfer cases, and we proposed a modified approach which is named as ARMO MS-DFT2. And in this method, we use the exchange correlation functional of the symmetrized transition density between each of these diabats to calculate this off-diagonal element. And this method is internally more consistent because in the limit A equals B, you will recover the Cohen-Sham energy of each of the diabat from here. And we benchmarked our method on a variety of hole and electron transfer systems. Let's first look at the whole transfer data set, the HAB11. And these are organic homodimers, which are fully symmetric. So one can accurately determine the diabatic coupling using high-level electronic structural calculation for the first excitation energy. And our method shows pretty good accuracy for these diabatic couplings in the whole transfer systems. The best performance is achieved with range-separate hybrid functionals, and even when moving to like a pure GGA functionals, the performance is not much worse. While looking at some other available methods, so the fragment orbital DFT method can also give quite accurate couplings, but they are not able to give give you variationally optimized diabatic states. And the constrained DFT method is pretty good for with range-separated hybrid functionals, but the accuracy somehow degrade significantly when moving to lower tier functionals. And if we use the original MS DFT scheme to couple the ARMO states, we will get a significant we will get a consistent overestimation of the coupling. And we also looked at the electron transfer cases. The data set is called HAB7-, and in general, the trends are very similar to the whole transfer case. And we also tested our method on asymmetric systems, so these two DNA base pairs. We found that our method can give consistent results regardless of the definition of the initial and the final states. And also in general, our method gives a best agreement with reference values. So our method meets all these goals, and we would like to extend this approach to treat photo-induced electron transfer. And this process will involve two different types of diabatic states. One is the locally excited state, which correspond to the electronic excitation localized on the donor species, and also the charge transfer state, which corresponds consequence of the charge separation process. So for the locally excited state, we introduced a method called ARMO delta SDF, which combines the variational optimization of ARMOs and the state targeting delta SDF method for excited states. And for the charge transfer state, if we only focus on the lowest one, then it can be obtained by the ground state unrestricted ARMO calculation, as in the cases of ground state hole and electron transfer. And the coupling between the LE and the CT diabatic states can still be evaluated using the MSDFT2 scheme. And we tested our method on a couple of systems. And here is the whole transfer in the Indo-guanine complex. And so here the hole can be located on the either the HOMO or HOMO -1 of the Indo molecule. So these two processes correspond to the ground and excited state hole transfer respectively. And our method can accurately predict both the diabatic couplings in both of these processes, in both the ground and excited state processes, quite accurately when paired with hybrid functionals. While we found that the original MSDFT method still overestimates the coupling, especially for the excited state case. And we also tested diabatization based the fragment charge difference diabatization method using TDDFT states, and it doesn't work very well for this system because TDDFT states are not of very good qualities for this open shell system. And we also investigate the couplings in the Pantone dimer, which is a key model system for studies of singlet fission. And the charge separated states, albeit having quite high energies, they are believed to mediate the conversion between the locally excited singlet states and the multi-exotonic states. And here we look at the focus on the coupling between the LE state and the charge separated state. The LE state corresponds to the HOMO-LUMO transition on one of the monomers, and the charge separate state corresponds to moving one electron from the HOMO of one pentasene to the LUMO of another. And we tested the coupling at many different intersystem distances and these monomer rotation angles. And in general, our method, the blue curves, have the best agreement with previously reported result using the XMC QDPT and the four-fold diabatization method. And yeah, so in summary, I have introduced the development of armor-based method to investigate non-covalent interactions and also electron transfer. So the extension of the armor EDA2 to the solution phase, salvation environment opens the door to the investigation of non-covalent interactions in complex environment, which can be used in many applications, such as like organic reactions. And the development of armor and the armor-based diabatic scheme we developed offers a way to cheaply compute DFT diabatic states, variationally optimized diabatic states from DFT calculations. And we are currently and accurately calculates the couplings between them. And currently we are using these diabatic states to investigate processes in condensed phase, such as electron transfer reactions. And with that, I would like to thank Professor Martin Hadgard, my PhD advisor, and Professor Tom Markland, my postdoc advisor. And also, I would like to thank all these co-workers who contributed to this work, especially Matthias and Paul for the EDA work, and Andres for the armor-based diabatization. And these two developments are supported by two separate NSF grants. And finally, I would like to thank Q-Chem again for giving me this award and the chance to present my research here. And also the method I just presented have been implemented or will be available in Q-Chem soon. So if you are interested, you can check out the most recent versions of Q-Chem. Thank you very much for your attention. Thank you.
Thank you very much. That was a very beautiful talk and lots of new exciting developments and features into Q-Chem that I personally am very, very much looking forward to them. So I would like to first make an announcement that some of you posed a question to Pavel's talks, many questions actually, which was in a question section that I was not expecting and not checking, my bad. And I was looking at the chat box, which I'm used to it. So nowadays there are different platforms, different features, so I should keep myself updated. So after Yuezhi's question and answer session, we go back to that question, so stay tuned. So if there are any questions, now I'm looking at both sections, chat option and question section. So please type questions that you have. They find it an awesome talk, both of them. Thank you very much. Hello, Yuezhi. Did you consider the solvation entropy and how did you evaluate?
So I think the solvation entropy is currently that is a quite tricky question actually. Yeah, so for the solvent, these implicit solvent models, what we get from the calculation actually the solvation free energy, which in principle should include the entropy, so because these solvation models failure to reproduce solvation free energy. Yeah, but I think for currently for the energy decomposition results I show here, they mostly I didn't do like some things like harmonic frequency calculation to calculate the reaction free energy. So these still more like the enthalpy calculation with correction with solvation free energy. So the electronic degree, so the electronic energy is still the is without the entropy correction.
Okay. So there are questions. The solvation interaction is not considered in ALMO EDA result. If calculation using solvation model is expectable to analyze solvation contribution to int, E and T, I don't know. Please, could you give comments? There is a follow-up question by the same person. Is it possible to assign fragment change and multiplicity for each fragment? Then merge both wave functions to obtain whole transfer also for the ground state and for the excited state. Then compare the energy contributions.
Sorry, so how many questions are here?
The first question is not clear to me. Let's answer the second question. Is it possible to assign fragment, charge, and multiplicity for each fragment?
I think so, yes. Yes, I mean, that's how the ALMO calculation is done, yes.
Okay, and then merge both wave function to obtain whole transfer, also for the ground state and for the excited states. I'm not sure I understand.
I think, yeah, that's possible. Yes, I mean, definitely you can, because this for diabatic states, you are supposed to assign like a charge and multiplicity for each of the donor and acceptor species. Yeah.
Another question: have you compared the diabetization results of your formalism ALMO EDA with constrained DFT on the same system? Can you comment how these two methods compare?
I did. I think so I did that for the ground state Hall and electron transfer cases. And so the constrained DFT result I presented here are using the default setup in Q-Chem. I'm not sure if the result would change in some other different code, like the implementation of constrained DFT. But here, what we can see is constrained DFT result give quite good couplings when combined with range separate hybrid functionals, but the result is really sensitive to the functional choice. And if you move to even like a global hybrid functional like a B3 lip, you get very large errors. And I think there are for the constrained DFT, there are many different ways to do the partition, and I wonder if the result would change if a slightly different partition method is used. Yeah.
Okay. There is a question. Can this analysis be extended to a strongly correlated systems?
Yeah, that's a very good question. Yeah, so for the ALMO EDA currently, I think Marlin's group is working on that direction, but I'm probably not so familiar with that. And I think currently what is done is the bonded EDA, which starts from like the high spin, like the high spin fragments, and then it flips the spin in the energy decomposition analysis to create a covalent bond. So this is essentially a EDA of like a cast with a cast 2-2 wave function. And yeah, and I think there are some development on that direction to extend the method to like multiple chemical bonds. But I think that work has not been finished yet. And also, I think there are many different answers for treating like strongly correlated systems, and for example, like a coupled cluster valence bond model and the method. And I think yeah, it will be interesting to further extend the energy decomposition to those cases. Currently, they are not available yet.
Okay, great. So we still have 5 minutes. So if you allow me, there are no further questions. I go back to Pavel. Maybe Pavel, you can turn on your camera and I read the questions, and then you can, because I'm very sorry, there were lots of questions for your talk. So one question is that for iron 2 complex, when you add 1 electron to iron 3, you always have 4 unpaired spins. Can you really ignore all configuration with more paired electrons?
Okay, probably the question is about the configurations which are not quintets, but the configurations with lower multiplicities. And for that, we run preliminary calculations to estimate where they are, and we see that they're higher than that. So the main contribution to the spin orbit splitting comes from the fact that the ground state, the ground quintet state, is degenerate, and it has different occupancies of orbitals that lead to the major effect in the spin orbit splittings, and the high level states and the states high in energy contribute way less. So, but from a very quick estimate of electronic structure, we saw that those states with lower multiplicities are higher. And
there are unfortunately no time to read all the question. I would like to read one question. In terms of magnetic coupling, it's broken symmetry approach applied in this study of copper oxalate. Is the case of orbital interaction of orbital coppers are not completely localized? Can you give some comments?
So I'm not familiar about broken spin studies on copper oxalate. I'm afraid I can't comment much on that.
Copper complexes tend to present a spin contamination. Is this problem solved with a spin orbit coupling included?
It depends on the complex. Some complexes indeed exhibit a spin contamination if we find the triplet state, and this is for dicopper complexes. But other complexes are fine and they don't exhibit a strong spin contamination. So I would say it is very system dependent. But in these particular calculations that I showed, spin contamination is not a problem. For the iron complex, S square was very small, and for the copper complex that I showed, I used DAP from the closed shell reference, so it doesn't have any spin contamination.
Okay, great. Thank you very much from both speakers. Let's virtually join me to thank them. It was a nice session. I enjoyed very much. And I would like to announce that the next call for Michael Wormit Award 2021 is until January 2015. So please send your nomination letters along with the necessary documents to the Q-Chem office, and also visit our new and very exciting Q-Chem website. So you will find all the information in the Michael Wormit Award tab. So I would like to close this session, and thank you very much from everybody to taking the time and being in this session with us.
This concludes our webinar. We would like to thank Cornelius for organizing, running, and moderating this webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.